In this video, I'm going to give a formal introduction to the torque model and how it should look like on the homework assignments. So for this example, I'm going to use the hanger lab that we did in class. So I'm going to draw the hanger here. And for this example, I'm going to have one force here called tension 1. And I'm over here, another force, tension 2. And what we're going to say, given tension 1, find tension 2 such that it does not rotate, or the angular acceleration, the rotational acceleration, if you want to call it that, is 0. So as you can see here, it basically follows the force model. So I'm going to draw an FBD. I'm going to sum the forces, and I'm going to add one little thing here. I'm going to actually sum the torques, which involves one more equation, and then we're going to solve. So it's basically the force model. So let's take a look at the FBD. So if we were to draw an FBD of this object here, we would have, as you can see here, T1, T2, T2, and then actually this object itself, the hanger, has a mass. So I'm going to list that as at its center of mass, mg, and at the pivot point right here, there's actually an F of n that holds it up. That's what holds the whole assembly up. So there's your FBD. So with some of the forces in the x direction, I see no forces that point horizontally, so that's 0. In the y direction, let's see, I see F of n minus mg, so the mass of the hanger, minus T1 minus T2, which makes sense because the F of n, if there's no up and down acceleration, if it's held in place by the pivot point, it's got to actually support the mass of the hanger and the two forces. So this is something that needs to be considered if you're an engineer and you're designing something where there needs to be a support. That pivot point in this example has got to be able to support all the forces. When we deal with rotation, there's one more equation we need to write. It's the sum of the torques. This is the Greek letter tau. And it's basically the rotational analog of force, the twisting force, any force that can cause a rotation. So as you saw in class, because these two forces, the mg and f of n, go through the pivot point right about there, any force that goes through a pivot point can cause no rotation. It's like if you try to rotate a door and you push through the axis or pivot point, you can't cause it to rotate. Only the T1 and T2 can cause it to rotate. So just as we define positive directions for forces, we have to define positive directions for torque. And so in this example, I'm just going to choose clockwise arbitrarily. And in later examples, you'll see there might be an advantage to choosing counterclockwise or so forth. This equals I times alpha. Alpha is the rotational version of acceleration, and I is the rotational version of mass. So as we'll see in class, the distribution of mass has something to do with the rotational mass, or it's an object's disposition to rotational or angular movement. At any rate, I see two things here. Now given my axes here and how I defined it, the T1 and T2, looks like T2, if I were just to let it act, T2 would want to make this thing rotate clockwise. So I'm going to give that a positive torque. I'll call that plus tau 2 minus tau 1. The torque associated with this guy here, if I were to let it go, it would want to rotate the object counterclockwise, opposite my reference. In this case, we want to solve for the forces such that it doesn't move, so I want 0 angular acceleration. We'll do one later where there is an angular acceleration, but for now we just want to maintain stability. So, to solve, I'm going to take my third equation, because this is my torque equation. I'm going to say tau 2 minus tau 1. These are not to be confused with tensions, because each one of these, if I equate them, is an R cross tension 2, and I'll say R2, and R1 cross tension 1. So you can see there is a distinction between tensions and taus. A tension gives rise to a tau. And as you saw in the lab here, we have R1, doesn't go exactly to that point, but and R2. And as you saw, the vector cross product is the magnitude of one guy times the magnitude of the tension times the sine of the angle between them, theta 2, which is, again, if you dot 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 this, that's the angle there. R1, magnitude tension 1, magnitude sine of theta 1, which again is dot 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 dot, and that's the angle here, theta 2. So if you solve for these guys here, tension 2 is equal to R1 tension 1 sine theta 1 over R2 sine theta 2. And so there's a first example of the torque model. So in summary, it basically follows the force model. We draw an FBD, we list all the forces, we sum the forces in the x direction, y direction. In this case, we add a third equation, the sum of the torques or sum of the taus. We define a positive rotation. In this example, there was no preference clockwise or counterclockwise, so I just chose clockwise. We sum the torques. It equals the rotational mass, which we call I, or rotational inertia, and the angular acceleration right here, I alpha. And in this case, we wanted it not to rotate, so we set it equal to 0, and then from then it's just a math problem. So these are the basic steps for a torque model type problem. In the next example, I'm going to show an example where things actually do accelerate and there is an angular acceleration given two objects.